As you can see from the titles on the board, this tutorial is about the properties of gases and what we call kinetic molecular theory. This chapter talks about gases and their properties. This is one of my favorite chapters to teach because it has a lot of everyday applications and there is a lot of really cool demonstrations that go with it. We'll break this down into 4 categories. The first video you'll look at is about properties and what we call kinetic theory. The second video that you'll see is about the different gas laws and their relationships. First thing, gases all possess certain properties. There are 5, and if you go to the handout section of the Chapter 10 on Edline, you can print out these properties. First of these properties is called fluidity. Fluidity is the idea that gases have the ability to be poured out of one container into another. What I have set up here are 4 bottles that have oxygen gas trapped inside. We did a lab like this in class, and if you weren't here, what we did was we used water displacement, right, to bubble water out of these bottles and let the gas replace them. I'm going to test this test tube for the property of fluidity. What I'll do is I will take a match and a wooden splint. I'm going to light this wooden splint and let it burn for a moment. In about 10 seconds, I'm going to blow this out so that it's glowing. And then we'll test to see if the oxygen that is inside of this test tube will be flowing out by putting the glowing splint to the edge of the test tube. If oxygen is flowing out of the test tube, we should see the stick relight due to the presence of oxygen and the combustion reaction that will occur. Let's take a look to see if that happens. Sure enough, oxygen flowing out of the test tube into the surrounding room, the splint relit. As long as there's oxygen that remains in the test tube and it continues to try to flow out, we'll relight. You can see by the fact that the splint now can go all the way inside of the test tube and not relight that all the oxygen that was inside of the test tube has since flown out into the surrounding room, and the test tube can no longer recreate the flame that was originally there. Second property that we'll look at for gases is that of expansion. If you read on your handout, you'll see that expansion is talking about the ability of a gas to fill whatever container that it is trapped in. If we have a 2-liter bottle of soda and I fill it with a gas, my gas's volume is 2 liters. However, if I attach a balloon to the top of that soda bottle, right, increasing its volume to say 3 liters, the new volume of the gas will be 3 liters because the gas will expand to fill the container. I'm going to test this bottle for expansion. First thing that I'll do is I will put a lit splint into the top 5 centimeters of the bottle. Right? If it relights, that tells us that there's oxygen present at the top of the bottle. I'll take it out, blow it out again, and then I'll put it toward the bottom 5 centimeters. If it relights at the bottom, that means that the oxygen has expanded to fill the entire container. Let's see what happens. So we take our glowing splint into the top 5. Sure enough, Relit, definitely oxygen present at the top of the bottle. Let's blow it out again, and this time we'll test the bottom 5. As you can see, the splint is continuing to burn brightly at the bottom of the bottle, proving that oxygen has expanded to fill the entire container. Third property. Third property of the gas that we'll look at is compressibility. If you look on your handout, it's going to tell you that gases have the ability to be compressed due to the fact that there is a large amount of space between the relatively small particles that make up the gas. To prove this to you, I'm going to take a miniature syringe. Using this syringe, I'm going to fill it full of air. Then I'm going to take a cap and put a cap onto the bottle. This isn't only one gas. If you remember from what we talked about, air is comprised of a lot of gases, the most abundant of them being nitrogen, oxygen, and carbon dioxide. Because this is a gas, I have the ability to push the plunger down to a certain amount. At the very beginning, the plunger reads all the way up near the 60 milliliter mark. But as I push the plunger down, we have the ability to get rid of the empty space that's in between those gas molecules, all the way down to, say, about a volume of 15 milliliters, compressing the gas down. What eventually stops the plunger is a mixture of a couple things. We get rid of all of those empty space between the particles, essentially turning it into a liquid or a solid, because now solids and liquids have their molecules tightly packed, no empty space. The other thing that starts to play a factor is as I push the plunger down, we tend to see an increase in pressure inside of this syringe, and as the pressure goes up, the ability to push the plunger down decreases. We will come back to the idea of pressure when we talk about our kinetic theory. Gases can be compressed. Next property I'd like to look at for gases is the idea of diffusion. If you look on your handout, it'll tell you that diffusion is talking about the random mixing of two gases. So I have two bottles here. One of these bottles I've allowed to be filled with air, just capping it to be safe. The other bottle is filled with pure oxygen, as was the other bottle in the test tube that we already tested. What I'm going to do is I'm going to allow these two things to randomly mix with each other. We'll do that by stacking the two bottles. If diffusion is going to occur, what will happen is the oxygen that is in the bottom bottle will flow and expand and diffuse into the air that's going on above it. So there's actually three different properties that are being tested here, but to prove to you that they mix, I will attempt to relight both bottles to prove that the oxygen is now mixed with the air. That takes a minute or two to occur, so in the meantime, we'll talk about the other part of the handout that goes with diffusion. This is called effusion, with an E. Effusion is talking about not the random mixing of gases, but a controlled one. One where I say inject one gas into another gas, where instead of not being able to control how they mix, I can control how quickly or how slowly those gases interact with each other through tiny openings. Enough time's probably gone by for us to check if diffusion has occurred. So again, I'll get myself a lit splint. Give this splint a second to burn. Allow it to be glowing. And first thing we'll do is we'll test our top bottle to see if oxygen has flown up into it. As you can see, the flame relights, proving that oxygen has made it into the top bottle. Blow this out so that it's still glowing. And this time I'm going to test the bottom bottle to see if we had air mixing in there as well. And you can see that burning very brightly, oxygen has diffused into both of the bottles, proving that air and the oxygen have the ability to diffuse. The last property we'll talk about of gases is that of low density. Gases have a markedly lower density than their liquid or solid counterparts. If you think about it, gases tend to float in many different substances, whether it be liquid or in the air itself. And if you remember from back at the beginning of the year when we discussed density, we said that floating and sinking has everything to do about something's density being less than or greater than another's. If something is going to float, its density will be less than that of what it's in. If it's going to sink, it will be greater than that of what it's in. We did a quick demonstration with the Titanic, and we talked about how as water filled into the boat, it changed its density, not allowing it to stay less than that of water's, and then the ship sank. We can do the same with gases. First, I want to prove to you that they do in fact have a lower density. Imagine three different phases of the same substance, like water. We know that we have ice, the solid phase, we have water, the liquid phase, and we have steam, the gas phase. If you take a look, I could go and put a bunch of ice into your bathtub at home. That ice would take up a certain amount of space at the bottom of your bathtub. If we increase the heat in your house, that ice would melt. It would still take up about the same amount of space at the bottom of your bathtub. Its mass wouldn't change, right? But its volume would remain the same also. If we turned your house into a sauna, though, the gas that resulted, the steam, would attempt to fill up your entire bathroom, therefore making its volume much, much greater and changing its density so that it's now lower than that of the water or of the ice that I originally put in. A more everyday application could be the function of something like a hot air balloon. If I were to look at how a hot air balloon works, you have the balloon on top, hanging from it, you have some flames, and then underneath that, you have a basket that holds the people. Now, the balloon eventually fills up to take up a large amount of space. But if you think about your density equation, if I want the balloon to rise and float in the air, its density has to become less than that of the air around it. So if you think about what a hot air balloon does, is it tries to lower the density both ways that it is able to do so. The first way I could decrease the density is by shrinking the numerator. For instance, 2 over 4 is much larger than 1 over 4. A half is bigger than a quarter. So if I can decrease my mass, I can lower the density. How the balloon decreases its mass most often is by building it with very lightweight materials. Right? The balloon itself is made out of a very mesh-like fabric that doesn't have holes in it, so to speak, but it's very lightweight. The wicker basket, right, is made of essentially hollowed straw. Right? So it's very rigid and it's sturdy to stand in, but they make it as light as possible. If you've ever been in a hot air balloon, it hangs sandbags on the side that when they're ready to fly, they release the sandbags, all of these decreasing their mass. The second way I could make this number small is by increasing the volume. If I increase the denominator, this number gets smaller. For instance, 1 over 2 versus 1 over 4. Right? 1/4 is much smaller than 1/2. So increasing the volume would also lower my density, allowing it to float. The gases have a much lower volume, higher volume, than their liquid or solid counterpart. So when I fill this balloon with gases, as opposed to when it's laying on the ground, it takes up a much larger volume. All of these help to explain why we can get a hot air balloon to fly. They also tie into this idea that gases have what we call low densities. These are all what we call physical properties of gases. As we transition into kinetic molecular theory, it has more to do with explaining a lot of these properties. The kinetic theory overhead is in a separate document, also in the handout section. If you haven't printed it out, take a second to do so, and we'll walk through these one at a time so that you can understand what's going on. Something else that should visually help you to understand kinetic theory is a website. If you go to Google, and in Google's toolbar, you type in Oklahoma State Gas Law Program, it should take you to a site that when you click on it, you will see a program that allows you to visualize what was happening inside the syringe that we were working with earlier. What it shows you is a container filled with many tiny molecules that are moving around. This is a very good representation of many of the assumptions that kinetic theory functions around. One of these assumptions of kinetic theory is that all gases are made up of tiny particles. Adding to that, these particles are very far apart compared to their size. We proved that when we tested for the compressibility that we talked about earlier. The particles are far apart, leaving a lot of space. That is why the plunger was able to go down. A second assumption of kinetic theory is that all of these particles are in continuous random motion. My drawing on the board doesn't do the justice that the website does. The website has all of these particles constantly moving around. You'll notice that on the website, one of the particles has a red dot inside. Over on the space to the right of the cylinder, you can click a button that says Enable Tracking. And if you do that, all of a sudden, the one with the red dot will have a line that you can trace. what you will notice is that there is no definitive pattern to the line that creates. That means that there is in fact randomness to the motion of the particles. Furthermore, you will also notice that the particles never stop moving. Third assumption of kinetic theory. As these particles move around, it is inevitable that they will run into each other and into the container walls themselves. We talk about something called an ideal gas. It conforms to all of our assumptions of kinetic theory. It says that every time one of these things run into each other, that the collisions are what we refer to as elastic. And an elastic collision simply means that no energy is gained or lost when they collide. This is in fact untrue. We know that when any two things collide, that energy has to change form. For instance, if my hands collide, energy gets given off in the form of sound and the form of heat. The reason we assume this to be untrue is so that we can use this to explain many of our properties. No theory is perfect, but if we follow these assumptions, we can explain a very many different things about gases. Fourth assumption of kinetic theory is that the speed of these molecules depends upon the temperature. Temperature and speed are related, as I described, directly, which means in math class, if they are directly proportional, as one goes up, the other goes up. If this is true, as I increase the temperature on a gas, the molecules should move faster. You can test this in this program by going over to the dials that lie to the right of your piston and dragging the temperature scale up. If you do that, you should notice a distinct increase in how quickly the molecules are moving around from each other. There is an equation that lets us put a relationship to energy. It says Ke equals 1/2 mv squared. Temperature and speed are directly related. V in this equation represents velocity, right? The speed that the molecules are moving. Another factor that can affect how quickly they move is the mass. Mass makes things move quickly or slowly depending on how large it is. Larger molecules tend to move more slowly. So the greater the mass, the slower they move. The less the mass, the faster that they move. This also ties into the property of gas that we talked about called effusion. The smaller a molecule is, the more quickly it is able to effuse and mix because they move faster. Larger molecules effuse more slowly because they are carrying much more mass through that opening. It is more difficult for them to move. Last assumption of kinetic theory is that all molecules have no forces of attraction or repulsion toward each other. Again, this is only in an ideal gas. We know that in the real world, molecules do have forces of attraction. We talked about them when we did bonding. Intermolecular forces like hydrogen bonding, dipole-dipole, London dispersion, and London dispersion is another name for van der Waals forces. When molecules get close, they do attract each other, but we pretend like they ignore each other so that we can keep this random motion intact. These different assumptions help to explain the properties of gases that we talked about before. To link those up, I just want to talk about each. Fluidity was that molecules pour out of the container. The reason they do has to do with this continuous random motion. If they are constantly moving around and there is no top to the container, like our test tube, they will pour out of the container, collide off the wall, and leave it. That is why they flow. That also explains why they have the ability to expand. All right? If they expand, it is because as the container gets larger, the molecules are not locked into place. They can collide and move to fill the entire container. We've discussed that the ability to be compressed comes from the fact that there are large spaces between the molecules. Assumption 1. They're able to diffuse because we assume that they are not so attracted to each other that they're bound together. They can intermix with other gases because there is no attraction forces to them, and because all the collisions are elastic. We didn't lose energy due to our collisions. The low density we discussed with the air balloon, but it has to do with all of these properties mixed together. The balloon is able to fill to a larger volume, lowering its density because it follows all of these assumptions. We will come back to all of these ideas to explain the gas laws, the relationships between the measurable amounts of these different properties of gases, but this should help you understand at least the theoretical end of things as we go through. I hope this helped you out. If you have any questions, please feel free to stop in and ask.